Hello everyone. We'll continue with our last lecture on linear equations. So if you just go around your daily life and try to solve some problems and just analyze the world around you, you'll see that you'll come across linear equations, or you'll come across the problems we encountered in our last lectures many times. And then you'll realize the need to have one common theoretical framework to address all these questions, and find an easier way to and have an easier way to answers those questions or find those variables. So in today's lectures we will develop a bit of theoretical framework on how to approach linear equations or a pair of linear equations, and then we will slowly strengthen these concepts with solving many different examples. Okay, so let's get started. So first, the general form for a linear equation, we write it as ax plus by plus c equals to 0. Now here we have a, b and c will belong to this set of real number. Now just to get a bit familiar with the symbols that I have used, this symbol represents belongs to. So these coefficients that we have here, a, b and c, they belong to the set of real numbers. And one more condition that these coefficients should satisfy is that both a and b should not be 0 at the same time. Another way to write it would be a square plus b square is not equal to 0. Now if you think a bit about this expression, a square plus b square, so a square will always be positive. No matter, unless a is 0, this term will always be positive. If it is a real number, then you can think on any number on the number line from negative to positive, and if you square it, it will always be positive. So for this term to be 0, a has to be 0, and same thing applies for b. For b square to be 0, b has to be 0. So in order for this expression to be 0, a square plus b square equal to 0, both a and b have to be 0. So this is just another way of writing that both a and b should not be 0 at the same time, because if both a and b are zeros, then you will just have a statement like a constant is equal to 0 or something like that, and we don't have a linear equation. Okay, so this is how we represent a linear equations. So you can write many numerous examples for it. For example, 2x plus 3y is equal to 17, y is equal to 2, x is equal to 5, 3x plus 4y plus 2 equal to 0, and many others. So these all are different examples of a single linear equations that we can have, that you will see. And now let's move ahead. Now what do we mean when we say solution to a linear equation? Solution to a linear equation. So if we try to plot a linear equation, let's say we have a linear equation, x plus y is equal to 5, and we try to make a graph for it. So this is our y-axis, this is our x-axis, and so in order to plot a straight line, we just need 2 points. So for this, let's say we have x, we have y as 5 minus x. So the first point that we take is 0, then we get 5. If we take x as 1, you get it y as 4. So first point we plot x as 0, y as 1, 2, 3, 4, 5. So something here. So this is our first point, 0, comma 5, and the second point would be 1 and 4. So 1 comma 4. Now we just have 2 points, and that is what we require for a straight line. So we just join these 2 points, and so this, sorry for my drawing, but yeah, this is a straight line, and then it extends in both directions. So what do we mean now when we say a solution to a linear equation? So this is a linear equation, x plus y is equal to 5. Now each and every point that lies on this straight line, for example, let's say this point would be x would be 5 and y would be 0. So this is a solution to this equation. This will satisfy this. Let's say we take another point, something here, 2. So x will be 2, y will be equal to 3. This is another solution to this equation. So basically all these points, all the points that lie on this straight line will be a solution for this linear equations. And vice versa, in other terms, you can say that the solution to this linear equation will be all the points that lie on this straight line. Okay, so just to formally state it, we have each solution xy of a linear equation in two variables ax plus by plus c equal to 0 corresponds to a point on the line representing the equation, and vice versa. So it's just what we said right now. For a linear equation, something like this, every solution that we will have, every pair of xy value that will satisfy this linear equation will be a point on this straight line. And saying it in the other terms, that each solution to this linear equation will be a point on the straight line. Any other point which lies outside of this, let's say, I don't know, 5, 6. So this point is not a solution to this straight line. If you plug in the value, 5 plus 6 will make 11, which is not equal to 5. So this point won't be a solution to this, and this point won't lie on the straight line. Whereas if you think of any point lying on the straight line, it will be a solution to this linear equation. Okay, let us now move to pair of linear equations. Pair of linear equations. So what do we have? So we had one linear equation. Now in a pair of linear equations, we mean we have a pair of linear equations. So first we represent it as a1x plus b1y plus c1 is equal to 0. So this is our first equation. Now it will always satisfy the condition that a1 square plus b1 square is not equal to 0, and a1, b1, c1 belongs to real number. So this will be our first linear equation, and the second linear equation will be a2x plus b2y plus c2 is equal to 0. So this will be our second linear equation, and it will also satisfy the same condition, a2 square plus b2 square is not equal to 0, and a2, b2, c2, they belong to the set of real numbers. So now above we saw that if we have just one linear equation, then it will be one straight line. So this is one straight line, this is another straight line. So when in the case of having a pair of linear equations, we will have a pair of straight lines. Okay, so in case of pair of linear equations, you may have three cases basically. So whenever you have two straight lines lying in just one single plane, there are only three possibilities. Either it may be intersecting, as in this case, or it may be parallel, or they may be coincident. So these are the three cases that will arise. Now when we say a solution to this, to a pair of linear equations, so by a solution we mean a common point, a common value of x and y, which will satisfy both of these equations at the same time. So in case of intersecting, there will be one and only one solution like this. So this value of xy will satisfy equation 1 will satisfy equation 2 as well, which means that xy is also solution to 1, xy is also solution to linear equation number 2, and thus xy is a solution to both. Xy is a solution to this pair of linear equation. In case of the parallel lines, we will have no solution. These lines are parallel, meaning that they will never intersect and there will be no common xy that will satisfy both of them. So there will be no solution to this. And in case of coincident line, as you can see, every point that lies on this line will also lie on this, will also lie on this. So basically what you have is each and every solution for one linear equation is also a solution for another linear equations. And instead of having just one solution, you have infinitely many distinct solutions for this pair of linear equations. Basically, they are just equivalent linear equations written in terms of, yeah, just a scaled up version or something like that. Okay, so there are some names given to these things. So when we have a solution to a pair of linear equations, we call it as consistent pair, consistent pair of linear equation. When we don't have a solution, we call it as an inconsistent pair of linear equation. And when we, so in this case, we already have a solution, so this already falls under the category of consistent, but there is a special name given to these kinds of this kind of situations where you have infinitely many solutions. They are called dependent pair of linear equations. So to formally say all of this, you have a consistent pair of linear equations whenever a linear equation has a solution. So in this case and in this case, you have a solution. So both of them are consistent pair of linear equations. Now there is one more category inside the consistent pair of linear equations when you have infinitely many solutions. So in the coincident case where you have many solutions, then we say that these linear equations are dependent. And in case of parallel lines, when we don't have any solution, it has got no solution, pair of linear equation has no solution, then we call it as an inconsistent pair of linear equation. Okay, so the first example that we'll start with is the example that we saw in our last lecture. So in our last lecture, we say how many times he played hoopla to be y, and the number of rides she had to be x. So the first equation that we had was y is equal to 1 by 2x, or x minus 2y is equal to 0. So this was our equation 1, and the other equation that we got was 3x plus 4y is equal to 20. So this was our equation 2. Okay, let us try to solve it using the geographical method. Let us plot it. So let me make the number line. This is our y-axis. This is our x-axis. So first let us plot the first line. So for equation 1, let us quickly write a couple of points. So x is x, y is x by 2. So if you take one point, x as 0, y will be 0. And if x is, let's say, 4, y will be 2. So we have 2 points. So the first point is 0 0, and the second point is x is 1 2 3 4 and y is 2. So we just join this straight line. This is our equation 1. This is our equation 1. Okay, let us try to plot the second equation. So we have x and y as 20 minus 3x by 4. So if we take 0, we get something, we get 0, 20 by 4 is 5. If you get 4, then you get 12, 20 minus 12, 8, this is 2. So the first point we have is 0, 1 2 3 4 5 0 5, and the second point is 1 2 3 4 2. This is the second point. So if we join this straight line, so this is our straight line for equation 2. And so now we have plotted the two straight lines. This is the straight line for equation 1, this is straight line for equation 2. Now in order to find the solution, we just need to have the coordinates for intersecting point. So this point is 4 2. So that's it. This is our solution. So x is equal to 4, y is equal to 2. 4 comma 2, this is the solution. Let us quickly plug in the value back here. X is 4, y is 2, so 4 minus 4 will be 0, satisfy equation 1. X is 4, 3 4s are 12, plus 4 times 2 8, 12 8 20, so it satisfies both of them. So we got our answer to the very first question. The number of rides she had, X was, she had 4 giant wheel rides, and the number of times she played hoopla was 2. So this is how we solve a pair of linear equations geometrically. We plot both of the lines and then we look at the intersecting point, and that will be the solution for it. Okay, now let us have a look at some more examples. Okay, so what do we have here? Romila went to a stationery shop and purchased 2 pencils and 3 erasers for C9, 9 cents or something. Her friend Sonali saw the new variety of pencils and erasers with Romila, and she also bought 4 pencils and 6 erasers of the same kind for 18 cents. Represent this situation algebraically and graphically. So just think about this in your mind. Like, there are 2 friends, Romila and Sonali. They went to a shop. Romila bought 2 pencils and 3 erasers, and the cost for her was 9 cents, rupees, whatever you want to think. And her friend Sonali also bought 4 pencils and 6 erasers, and she had to pay around 18 rupees. So the thing we need to find out is what is the cost of pencil and what is the cost of eraser. So these are our 2 variables. So let's say we just assume, so what we don't know, cost of pencil as x and cost of erasers as y. Okay, so first let us try to write the case of Romila. So Romila bought 2 pencils, so 1 pencil cost x cents, then 2 pencils will cost 2x. And she also bought 3 erasers. 3 erasers and multiplied by the cost of 1 eraser will be 3y. And both of this will be equal to 9. So this will be our equation 1. Now for Sonali. Sonali bought 4 pencils. So 4 pencils, 1 pencil cost x, so 4 pencil will cost 4x. And she bought 6 erasers, so 1 eraser cost y, so 6 erasers will cost 6y. And both of this together summed up to 18. So this is our equation number 2. Okay, so for the first equation, let us write some points. 2x plus 3y is equal to 9, so x, y will be 9 minus 2x by 3. If x is 0, 9 by 3 will be 3. If x is 3, 3 multiplied by 2 is 6, 9 minus 6 3, 3 by 3 is 1. So we have these 2 points. So the first point was 0, 3. So this is our first point. The second point is 3, 1. So these are our 2 points. We just join them and we get our first straight line. So this is our equation 1. Now for equation 2, again we have 2 points, 0 3 3 1, 0 3 3 1. So we have the same points essentially, so basically we have the same straight line. Sorry, this should be exactly on one top of another. Okay, so what do we have here? We have a case of coincident lines. So basically they are just the same. If you have a look here, if you just multiply the first equation by 2, you get 4x plus 6y is equal to 18. So this is the case of a dependent pair of linear equations. So there could be many solutions to it. Maybe the pencils cost 3 cents and the erasers cost 1 cent, something like that, or yeah, the pencils are just for free and the erasers are costing 3 cents. So with the given amount of information that we have, we cannot answer exactly what is the value of uh, one pencil or one eraser. It could be it has infinitely many different possibilities. Like what exact value could it be? It could be this point, it could be this point, this combination of xy, this combination of xy, or anything that you can imagine here on this straight line. So all these points on this straight line will be a solution to this. So this is a case where sufficient information is not there to exactly answer one value for x and y. So this will fall into the category of dependent. I mean, it is also consistent because it has one solution. It has at least one solution. It has finitely many solutions. So this will be a dependent pair of linear equation. Okay, let us have a look at another example. So we have two rails or two railway lines. So one of the railway lines is represented by equation x plus 2y minus 4 is equal to 0. This is equation 1. Let us quickly represent it in a number line. This is x. So if we have, let's say, x and y is 4 minus x by 2y, y is 4 minus x by 2. So if you have x as 0, you have y as 2. If you have x as 4, you have y as 0. So we got our 2 points. So x is, let's say, 0, 1, 2. This will be our first point. So this will be our first point, and then we have 1, 2, 3, 4, 4, 0. This will be our second point. And if you just join these straight lines, this is our first line. Okay, this is our equation 1. Now for equation 2, what we have is 2x plus 4y minus 12 equal to 0. So if we quickly write for this one, we have x, we have y as 12 minus 2x by 4. If you take x as 0, you get 3. If you take x as 6, you get 0. So we have 2 points, 0, 1, 2, 3. This is our first point, and 1, 2, 3, 4, 5, 6. This is our second point. So if you carefully draw this properly with a proper graph and using a scale, you will find that both of them are parallel lines. These are parallel lines. I'm sorry for the drawing, but if you draw it properly, you'll get these at parallel lines. So what does this mean? This means that equation 1 and equation 2, they do not have a common point. They do not have a common x and y which will satisfy both of them. And thanks to these two trains will never collide with each other, which we see sometimes happen in our real life situations. But these two paths are designed in such a way that they are parallel to each other and they will never intersect each other. So this will be called an inconsistent pair of linear equation, meaning that it has got no solution. Let us quickly summarize what we learned today. So we learned quite a lot. So we started with a single linear equation, ax plus by plus c is equal to 0, and then we saw that it will represent some kind of straight line on a number line x and y axis, so it will represent some kind of straight line. Okay, so in case of a pair of linear equations, the three different situations that we could have is, first, what we saw in example number 1, we could have a pair of straight lines intersecting at one common point. In this case, we have one unique solution, and this was called as a consistent pair of linear equation. In example 2, or rather example 3, in the case of two railway lines, we saw that the lines are parallel and there is no common solution. So it is called an inconsistent pair. And in our example 2, we saw that the lines are coincident. So we have infinitely many solutions. So this is called dependent pair of linear equations. So it is also consistent because it has at least one solution, but since it has infinitely many solutions, so it is called a dependent linear equations. So basically this is what we did today. A pair of linear equations represent two lines and there can be three different cases. So thank you very much for this lecture, and we will continue with linear equations, solving some more problems in the lectures to come. Thank you.